Hey, it's your friend Israel again with this presentation on using a nice multi-thread um, power algorithm to generate prime numbers. So we are going to use the POSIX threads, and usually called the Pthreads library in C++. And so the goal of this research, this project was to um, demonstrate fundamentally parallel programming concepts, how to create threads, manage their life cycle, handle their results, and understand the performance of the characteristics of a simple parallel algorithm. Now, it wasn't built to determine the fastest or most efficient prime number finder, but rather to demonstrate the fundamental power programming concepts. All right, so the core idea is straightforward. Um, we launch a squad of 100 worker threads, and each one independently hunts for a prime number by checking up to 10 randomly generated very large numbers. So you're looking at very large numbers. Okay, now let's dive into the code. So up here on my screen, I have my manual steps. Okay. Okay. So basically, first, no, first is our usual library. We include the library, and then we define our key constants. So here we define our key constant. We have 100 threads, and then the maximum number of attempts is 10, and each we are to generate a number that can be as large as 10 to the power 17. And that's when we have those right here. Okay, so the heart of this computation is the next step, this part. There is prime function, which is used to determine trial. It uses a deterministic trial division algorithm. Okay, so here the key content is this, that if a number is less than 2, then it will rule it out. So it immediately rules out numbers less than 2. And we say that the first prime number is 2, right? So if number equals 2, return true. And then it filters out all even numbers, or it takes them all out, because most even numbers, in fact, except 2, most even numbers, all even numbers are not prime numbers mathematically. All right. Okay. And then for odd numbers, so in this part, for odd numbers, it checks for divisibility by every odd number from 3 up to the square roots of each number or each candidate. Right. So it's going through here. So basically, except 2, which is an even number, all other prime numbers are odd numbers. Right. Okay. All right. So no, don't forget, this is a nice method for a number close to our upper limit. The square root is about 300 million, meaning in the worst case, this loop will run 180 million times per candidate. This intentional inefficiency is what makes the problem computationally interesting and worth parallelizing. Okay. All right. So we're done with the first part. Now let's go and hands for the prime numbers. Okay. So let's see what each local thread does. For the function, hands for prime numbers is the entry point for every thread. So here we are receiving a unique thread ID, and each thread enters a loop for maximum 10 attempts, right? So there's the thread ID, then a maximum random value right here, okay? Then the success path is prime, so right here. So maximum attempt, sorry, let me go back. So here we are hunting for the prime numbers. We receive a unique thread ID to ensure thread safety. All right. And then we enter each thread enters a loop for a maximum of 10 attempts. So again, a maximum of 10 attempts right here. And each attempt generates a random candidate number within a massive range. Okay. Now our success part is this part is prime and returns true. The thread prints a success message. It prints a success message on which track we find the prime number on which track we call it. Okay. And for the failure, we coming down a bit. So for the failure, right here, it's like if it exhausts all 10 attempts without success, it prints a failure message and exits, returning the null print right here. Okay. Now let's go to the main parts of the program. So for the main parts, just a moment. For the main function, it acts as the coordinator. Its job is to create the threads, wait for them to finish, and then collect all the results. So we have the creation phase right, right here, where it's created. Then we launch the web of threads, right? And then when we have to join, we join, and then we gather results. So here's where we are gathering, we are joining, right? Okay. We are joining. So after creation, the main thread calls pthread join on each worker thread. This is a blocking call that waits for the thread to terminate. Okay. So the second parameter is pthread join, captures the thread's return value, which is either a pointer to the prime it's found or null point. And then the next is okay. So right here, we aggregate and clean up. We aggregate and clean up. So right here, we have our summary. Then if we strike gold, it's a mission accomplished found, blah, 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 blah. All right, so let's exit and then run this code. So this is my bash. And then this is my boom. So you see the number of attempts. Here, the worker threads are launched. All these numbers. So we are gathering results from all the threads. So if it is exhausted without finding a prime, some is strike gold, some is not strike gold, and this is my summary. So we found 26 primes using 100 threads. Success rate is 26%. Okay, so how did we learn from this code? The performance, the runtime is highly variable, depends on luck. So how quickly threads stumble upon prime numbers. The prime number thread tells you that near 10 to the power 17, about 1 in 40 numbers is prime. So we expected a success rate of around, say, give and take 22.5%. But in our case, we got a 26%, which aligns with our test runs, right? The few bottlenecks, we have the zero square roots and primality test. This is a CPU bump, and which is I do for multi-threading. On a multi-core system, we see a significant speed up compared to a single threaded version. So the strength of my code, using a thread local random number generators, you avoid all contentions. The only shared resource is the STD C output, which has internal locking, so output something gets interleaved, but the program does not crash. Then we have a careful dynamic memory management, which ensures we have no leaks. So for future works, since this is a naive implementation, to improve with a more efficient parametric tests like Miller Robin or dynamic work queue instead of a fixed number of attempts per thread. So in conclusion, this project successfully demonstrates the core mechanics of multi-threaded programming with few threads. We've seen how to decompose a problem into parallel tasks, simpler tasks, multi-thread lifecycle from creation to joining and safely communicating back to the main thread. Right? So while it's simple, it provides solid foundation for understanding more complex power systems. Thank you. And this will be it now. Yeah. And if you have any questions, you can just put in the comment section. I hope to hear from you soon. And see you again next time. Bye bye.